I want to talk to you after class. You know, there's this guy on Facebook. He's got his name and first and last name. And he's your account. Is that your uncle? I'm like, all right. I got a standard African. It's like asking
It's like about 60% of the men in Jamaica are named George.
right,
What do I
yeah.
Right. Okay.
That's a stereotypically.
Yeah.
All the
Is it?
That's one of the tertiary. I mean, it could have been worse. I mean, maybe something like Nebuchadnezzar or something.
Yeah. I guess that one that was like profoundly biblical.
Yeah, no, you're just like tertiary.
It's just one of those characters the son of, you know.
All right. So the recording has started. So I'm going to get started with the class. We have already started to talk about the stack pointer. We talked about the push instruction, the pop instruction. Okay, so and I implemented both as a C subroutine as well as the instructions. We went through GDB to illustrate what happens to the stack pointer, what happens to the memory area pointed to by the stack pointer as we push and pop. Okay, so those were the things that we did last week. So what we'll do today is kind of move on and talk about the call and the return instructions, which are also based on stack operations. And once again, these are all cisp instructions. In other words, they can be done using simpler instructions, but they are also extremely handy to have, you know, as individual instructions. So we kind of like that about call and return. We'll talk about the make program. Okay, the make program is a very useful utility program. For those of you who have been using GUI tools in C and C++, you have been missing out on, you know, the fantastic make utility program. So in this class, we'll talk about it a little bit, and you know, there's a link to an actual template of a Makefile, so we'll make use of that one. The reason why we will talk about a Makefile is because we will start to write subroutines, okay? Because without call and return, well, it's kind of hard to write subroutines, to write functions. But without functions, you know, we can only write code that is up to a certain complexity level, because without modular programming, which is what the functions are about, it becomes kind of difficult to break a big problem into smaller problems. So we'll be writing subroutines, and that's why we need a Makefile, so that we can break a big program into several smaller source files, and then have the Makefile to do the right thing and only do the minimum necessary recompiling or reassembling, and then just relink everything. Okay, so we'll talk about the whole concept of how to use a Makefile. We'll talk about what a call frame is. I'm just moving down the list here. Well, jumping a little bit in between. We'll talk about a call frame. A call frame is kind of a very important concept because every C and C++ subroutine has a call frame per invocation. Okay, it is something that is created on the fly, on the stack, and when the subroutine is called. When the subroutine returns, it disappears. It is very important because it contains the parameters when you call a subroutine. It contains all the local variables, and it also contains other things for bookkeeping purposes that we don't even, there's no, quote unquote, no name in C and C++ program. This particular topic, okay, call frame, local variables, return values, and stuff like that, these are extremely useful, I think, not in this class, okay, because most people think about assembly language programming and go like, why do we want to program in such a low-level programming language when we have all of these, you know, fantastic tools so that we don't have to do all this stuff? Well, understanding this part here will help you debug programs in C and C++ when you look at the behavior of a program and go like, there's no way a C program can behave this way, and yet it does. Why? Well, it's because of memory corruption. But memory corruption of what? Once you understand the call frame, you will start to understand, oh, so if I corrupt this thing over here in a certain way, the behavior of the program is going to go like this, which is completely weird and strange if you did not understand the underlying, you know, memory allocation of a call frame. So that's why, you know, this topic is almost the only part that you can almost take immediately out of this class and utilize it in your other programming classes. As long as you're still using C and C++, I think many of these topics will still be useful.
So will this help us understand like the buggy programs at the beginning?
Yes, it will. You will understand that, and if we have enough time, we can even go and try to write an exploit. Yeah, write a little Stack Overflow exploit, and actually see how it can be done. Okay. And if you want to look into that sort of thing, you can just look it up. There are a lot of literature out there, tutorials and whatnot that can help you understand, how to make it happen. So it depends on how much time we have. We may or may not be able to get to it. Okay, so I'm hoping that we will be at least be able to get to some of it. Okay, because it takes a little bit of crafting. Okay, to make that exploit. But the principle of an exploit is actually very simple. It takes a lot of chore and a lot of time to craft it, but to understand the concept is actually not that hard. Okay? All right. So to motivate people to pay attention in class and so on and so forth, we have a homework assignment as usual.
Motivation.
Well, this is a program in C for the most part, at least for the time being. And the program is called interface, or homework assignment is called interface with C. In other words, not only are we interested in writing subroutines, we want to write subroutines that your C program can call, C or C++, okay? And eventually we'll be doing the opposite as well, okay? We want to be able to call C and C++ subroutines from assembly language, okay? And it's not that hard, okay? It is actually simpler than we thought it would be. So if you look at this program, or this homework assignment, it's fairly easy. In your follow these instructions, read the notes, and pay attention in class. Okay, so those are all the usual stuff that might be helpful. In a home directory, create a folder called CIF, which is C interface. In this folder, create the following files. The first one is main.c, which is just a C source file, and then the second one is called a Makefile. I'll explain what the Makefile should look like. It's not in the homework description at this point. The C source code has a few subroutines. Okay, it has a subroutine called Johnny, has a return type of int, and it returns a value of 5. Are there any questions about the behavior of this subroutine when it's called? Okay,
It desires it.
that's very good. I don't have to send anyone back to CISP 360 or earlier. What about this one here? One more.
I don't know.
Yeah, what's going on?
I think you go back to algebra.
It's well, it just returns whatever x is plus 1. Okay, that's all it does. It does not change x. It just returns a value that is x plus 1. Okay, so pretty simple subroutines. No big deal in terms of understanding what the C code means. Okay, so in the main program, which is the part where you can test the subroutines, is we have a local variable x in main, and the first thing we do is we call Johnny. We take the return value of Johnny, store that into x, and that's the first statement. Any questions about this one? Does anyone know why I call that subroutine Johnny?
John 5.
Yep, and that comes from which movie?
Short Circuit.
Short Circuit. That's
Short
right.
Circuit.
And Short Circuit 2. Yeah. Johnny 5 is alive.
Cool.
Yeah, that's a terrific movie. At least given how old the movie was, it's actually pretty good. So the second line, is going to call one more, okay, which takes one parameter, and I use local variable x to specify parameter x. When it returns, it will return, basically a value of 6. Store that back into the local variable x, and then we get to the return statement in main, and the whole thing concludes. Okay, so this is not a complicated program in any way, and I don't really want it to be very complicated because I just want you guys to get started with all this stuff about what do we do when we want to implement a particular thing in assembly. So what you want to do is to update the Makefile. I will give you the link, and I will explain how it works. Update Makefile to compile the source code to an executable called main. You will need to use GDB to test this program because it has no input or output in this program. There are no printfs, there are no couts, no nothing like that. It is just working with variables. Are there any questions about testing this particular program using GDB? How would you test this program? If I want to see how X of main is getting updated, how would you, use GDB to test this program? Set up breakpoints, okay, examine the value of X before the call, execute the statement after the call, look at X again, that would be, how you can test this program. Okay? All right. So once you verify this program does work as what you expected, as what you expect in C, then it is time to turn it into assembly. So I want you to turn Johnny and one more into assembly code. But since these are subroutines, I want one file per subroutine. So I want the first file to be named Johnny.uppercase and the second file to be one more.uppercase s. The extension in this case is necessary because of the way the assembler works. So we're going to use GCC to trigger the assembler, and as a result, the extension is important because that is what is telling the compiler what to do, how to translate it into object code. So once you do that, you also want to comment out the function definitions in main.c, otherwise you will have a duplicate definition of the labels. So you have to do some editing in main.c. You also need to update the Makefile in order to make use of the assembly code instead of the C code. Okay, so you need to convince the Makefile and say, hey, we have these labels defined in these other files already at this point. In GDB, you should test main in C and observe that the program does behave the same way as before. You can use n, which is next, to step over a function call if you don't want to step into the function itself. And when everything is said and done, use the following command to create the submission file and turn it into Moodle. Okay, so that's your homework assignment. All right, so what we'll do today is I'm just going to go through a sample program to illustrate something kind of like this, okay? And in the process, we'll also be explaining what is call and what is return, okay? So it's kind of like one single class to explain multiple concepts, but those multiple concepts are all related, and that's why it's all grouped into one single class. So are there any questions at this point? Okay, no questions at this point. So we'll start with doing something kind of like this, okay? How do we return a value? How do we call a subroutine first, okay? How do we call a subroutine? How do we return from a subroutine in assembly? That's the first thing we have to basically deal with. And I can use this program to illustrate those concepts. In other words, I know that this call here to Johnny is over here. So execution will continue in the subroutine Johnny. It will return 5, actually does two things in C and C++. The first thing it does is to specify a return value of 5. The second thing it does is to go back to whoever called this subroutine to begin with. So the big question is, okay, the value of 5 is, well, as we'll see, is pretty easy to deal with. But the big question is, how does it know that we should go back to x equals to Johnny and finish what is left to be done on that line, which is using the return value of Johnny to update local variable x? That really is the big question. What do you guys think? Well, the stack pointer is involved, but the stack pointer all by itself is not enough to do it. In other words, before we actually continue execution in Johnny, someone has to leave behind something to remind itself, hey, when we're all done, this is where we want to go back to. Go ahead.
I was just going to say that there has to be a base pointer, which is going to say this is where we started at, and then the stack pointer keeps track of how far we've gone. So
Yep.
we just want to subtract back to the base pointer.
sort of. The stack is used to store that quote-unquote pointer. Yep. Go ahead.
Call frame.
Call frame, well, we don't call it a call frame at this point because it's just a simple return address. Okay, but the concept is a return address of where do we go back to when the subroutine is all done. Okay, that is the concept. So what we'll do is to explain, the two instructions that are really useful for this. One is called a call, and the other one is called a return. Okay, those are all actual instructions. So I'm going to make this little program here called call return.s. This is lowercase s, which works in this case. And so we'll just go ahead and write this rather simple program. And here we'll just call f as the subroutine, and we'll do something which is nothing here, and we'll call f again. And then we'll do the usual sequence of exiting a program. Okay, and in assembly code, you can define the label f anywhere you want. Unlike in C and C++, where the definition or the prototype has to appear before the actual call, in assembly, it doesn't matter. Okay, you can make the call before the actual definition of the subroutine.
I've noticed that you've been using decimal for the first two, then hex for the last one. Is there a particular purpose for that?
For this one, it is just conventional to be 80 in hexadecimal because when we look at a jump vector, most of the time we use hexadecimal for that purpose. It's kind of more of a conventional thing. The other thing is, 1 is 1 regardless of the base. So 0x1 is kind of extra typing for no particular benefit. All right, so here's the subroutine f. Hey, we know this. We know what a colon is supposed to do. What is it doing?
Create a label.
It's defining a label. It's just basically saying, oh, okay, this is f as a label, and it's defined to be the address of this location. In other words, it is serving the same purpose as underscore start colon, which is the definition of a label. So that means to define a subroutine called f, all you have to do is to say, oh, here's the entry point of the subroutine, and it has the same label or the same name as the function name itself. Okay? Fine. And let's just say that we don't really need to do much here, so I'm just going to use no op as a spacer just to be sure that, yes, we got into subroutine f, and we have a return statement here. Okay? Yep.
I figured there's differences inside, but so since f is just a label, hypothetically you could just jump to that instead of using call.
That is correct. Okay, if you just want to end up executing on line 13, okay, you can just jump to it. But the big difference is if you do a jump into it, it doesn't know how to get back to where it came from.
So call
Jump.
sense that.
Call is a little bit more than just a regular jump. It does what a regular jump does too, so the call instruction on line 4 as well as line 6, it will continue execution at the label f, just like an unconditional jump is going to do. But it's also going to do something else that has to do with the stack pointer and also the stack itself. Okay. So this program is kind of done at this point, but not entirely, because I want to give line 5 and also line 7 a label, just so that I can, I have a way to refer to those locations. Okay, because it is going to be kind of useful, those particular locations. And that's what I'll do here, and I'll just call those. They don't really need any particular name. I'm just going to call this L0, and I'll just call this one L1, just so that I have a way to symbolically refer to the address of the no op on line 5 as well as the move L on line 7. Are we doing okay so far? Is that okay? All right. So let's go ahead and assemble this program. Link it. And use GDB to take a look at what happens when we run this program. Okay? And we'll put a breakpoint on line 4, which is the first instruction of the entire program. and start running it. Okay, so this is right before we do the call F. As I said a little bit earlier, the stack pointer is useful in this case. So we'll go ahead and examine the stack pointer just to see, okay, but what is the content of the stack pointer? What is the address that is being stored in the stack pointer at this point? This is one way to do it, okay? Not the only way, just one way to do it. So at the entry point of the entire program, before the call instruction, the stack pointer ends as ends with 40, okay? Because it's not going to change all that much, okay? All we have to do is to keep track of the least significant 2 digits. Now we single step with the call instruction. Single step, and quite not surprisingly, we end up in the subroutine because the no op on line 13 is in the subroutine itself. And as somebody said a little bit earlier, a jump can do exactly the same thing. A jump will continue execution at wherever the label is. So how is this any different? But remember what I said about the stack pointer? This is going to use the stack pointer. It's also going to change the content on the stack. So let's take a look at what is happening here on the stack. First thing is to print out the value of the stack pointer. And what do you notice? It is 4 bytes smaller than before. In other words, it is now pointing to a location that is 4 bytes below where it was. Can someone tell me, does that mean the stack just got smaller? Because the stack grows down, okay? The smaller the stack pointer, the more stuff you have stored on the stack. In other words, we just store something on the stack, okay? Or at least there's good suspicion that we just store something on the stack. And do you still remember the definition of the stack pointer? Where does it point to? It points to the last byte of the last thing that we store on the stack. It was 40, and now it's 3C. So that kind of implies that the location 3C, 3D, 3E, and 3F, those 4 bytes, is storing something new because of the call instruction. Because that's the only thing between the stack pointer ending up as 40 and ending up as 3C here. Okay? So we'll go take a look at what exactly is on the stack at that location. Okay, BFFF FA3C. And the command to do that is X command examine. We want to examine one thing which does not need to be typed. If you don't type a 1, it is just implicit that you want to type examine one thing. It's 4 bytes long, so I'm going to use W, which is a word. I want to display in hexadecimal, which is an X. And if you want to, you can do it this way to specify I want to go to the address of where the stack pointer stores, or you can just type up 0xbFFF-FA3C. It's entirely up to you. Or you can even use $2, because $2 is also representing the value printed by the previous print command. So all of these methods would work pretty much the same way. Okay? But just to be sure that we are looking at the right location, just for this time, I'm going to use 0xbFFF-FA3C. Press the enter key. Well, looks like some kind of random value here. 08048059. Remember we had a label L1, label L1, L0, and L1?
L9.
Okay, so we'll take a look at one of those and see if it has any relationship with this particular thing. So we'll go ahead and say print. When you print a label, you have to use the ampersand. That's kind of like it has to do with GD being too smart and try to interpret things with types. And a label really does not have a type, and it's trying to force it to have a type. So we have L1, L0, and L1. We'll display L0 first. What do you notice? It is the same. So the address that is represented by L0 is stored on the stack because of the call instruction. Now what is significant about label L0? It's right after the call instruction. Now why is that location important? So after we are done with the subroutine, okay, we know where to go back to. That's exactly the mechanism of call. Okay, so what it does is the first thing it does is to store the address of the instruction right after the call instruction. Then it will do an unconditional branch to the label. Okay, and it has to order in that particular order.
Yeah.
Okay. So then what we do is we single step the no op instruction in the subroutine, and now we're at the return statement. The stack has not changed at this point, okay? In other words, I can double check just to be sure. The stack pointer has not changed. What the stack pointer points to has not changed. Are we still doing okay so far? The no op instruction doesn't do a single thing. All right, so when we single step, where do you think we should go back to? We should go back to label L0, okay, which is also the address that we have stored on the stack, okay? So we single step, and just to be sure, we went back to line 5, exactly where label L0 is. Wow. That just took all the magic out of calling and returning from a subroutine, doesn't it? Because now we know exactly how it is done. What about the stack pointer? What do you think should happen to the stack pointer at this point?
It should be higher.
It should be back to 40, okay? Because once you use a return address, it doesn't really have any use on the stack anymore. So it should go back to 40. We'll double check. It does go back to 40. So now we single step through the useless no op instruction. We are now ready to call again. So this time it should not be surprising at all. Okay, the call will go into the subroutine. When we print the stack pointer, it should go back to 3C. Because this is the second call, it's going to reuse the same 4 locations to store the return address for this invocation. We look at the content on the stack at this point. It is now a 5F something, okay? What do you think, which label do you think will correspond to this address? L1. Well, we just want to double check, and it does, okay? Because that is really the return address. So we single step through the no op instruction in the subroutine. Now we have the return instruction. The return instruction goes back to line 7, which is where L1 is. Is that okay? And the stack pointer is now going back to 40, because those 4 bytes on the stack storing the return address is now of no use anymore, and they get deallocated. All right. Are there any? Yep, go ahead.
No, I mean, sure. But so, without that, how would we?
Without what?
Without the call mechanism, how would that happen? Like,
Well, that's a very good question. We'll actually get to it when we're done with this particular program. So we are just about at that point. Go ahead.
The stuff we did put on the stack, and after it came back, is it actually still there though?
That is an extremely good question. Okay, so the question was, the stuff that we put on the stack, which is 804.805F in this case, is it still on the stack? Okay, the answer is, because Linux is a protected mode operating system and the system itself has its own stack, the answer is yes, it is still there. But it is not in general true for different types of operating systems. Okay, we haven't really talked about hardware interrupts yet, which is a concept that will kind of throw a wrench into this belief that content on the stack will stay quote unquote intact even after you pop something or after you adjust the stack point. Okay, so the first thing I want to do is just to show you that first, and then I'll go back and kind of explain a little bit of what I mean by that. But you can see that even though the stack pointer is now at 40, the content is still there. Now the main reason is to overwrite this with all zeros or whatnot takes time. And that's really time wasted. Why would I want to destroy something when there's no need to destroy it? Okay, because it's just quote unquote deallocated. I just move a line to basically say this side is in use and this side is unallocated. I just move the line over and say, oh, we now have more stuff that can be used when we need to. That's all the pop instruction is doing. Okay? So I want to go explain, since we are here, it is probably a good time to talk about interrupts a little bit to address your question, because if I introduce interrupts in a different setting, then we're not in the same context anymore. Okay? So the question is this. Okay, this is the stack. At some point, the stack pointer points here, and then we have a pop instruction or a return instruction, and the stack pointer is now changed to point to a higher location. The big question is, when the stack pointer is pointing to a higher location, what about this stuff here? Is it gone? Should it still be here? What is guaranteed? Well, the answer about the guarantee is there's no guarantee, okay? So even though when we observe it's still here, that's only because interrupts do not affect what we call the user stack. It only makes use of the system stack, okay? So now we have to kind of explain what is an interrupt. If I want to describe an interrupt in 2 words, I would just call that a hardware subroutine. It's a subroutine that is called by hardware, not by software. But why would hardware want to call a subroutine? I mean, hardware should just do what hardware do, and why would it do anything with a subroutine? So here's a little digression, which means we may not be able to actually start the homework assignment, okay? But it is important. This is an important concept. So let's just say that I'm in my office, and it's my office hour, and the job of my office hour is to answer your questions, right? So I'm sitting in my office. I have no idea whether somebody is outside or not, okay? But just in case someone is outside and is just quiet and not saying a single thing or making a sound, I'm going to say, hey, is anyone outside? Can I answer your question? Even though there's no one in the hallway, which is 99.9% of the time during my office hour, okay? Nobody came back with an answer, okay? And I can have a little timeout here, type of mechanism, and say, if there's no response in 2 seconds, it means nobody is waiting outside. So what do I do after 2 seconds? I time out. I come to the conclusion that nobody's outside. And then what do I do next? I call out again, okay? And say, hey, is there anyone waiting for me in the hallway? If so, I'm available, come on in. After 2 seconds, nobody responds, and I'll ask again. This mechanism is called polling, P-O-L-L-I-N-G, polling, okay? Now polling is a very simple mechanism, okay? It's very easy to understand, and it works really well with DOS. And since we were talking about Tron, it came from CP/M. CP/M is the operating system while Tron, the movie, came out. And does anyone remember what is the name of that evil program that was trying to take over and control everything? Master Control Program, MCP. Do you notice any relationship between the evil operating system in Tron and compare that to the predecessor of DOS, which is CP/M? Yep. I'm pretty sure that was intentional. So anyway, so CP/M being the predecessor of DOS used a polling mechanism. But why would an operating system want to do anything with hardware?
So right off disk.
Well, the first thing is the keyboard, right? Go ahead, sorry.
Right off disk.
Reading a disk, writing to a disk. But back in those days, well, the keyboard is the first thing that comes to mind, right? Because CP/M, just like DOS, has a prompt and waiting for you to type something, right? When you enter a command, then it will go to the hard drive and do something, maybe, right? Okay, so it's using a polling mechanism. In other words, CP/M never goes to sleep. It is always asking this question. Hey, is there a keystroke for me to process? 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 And it'll keep asking that question until there is one. Then it will process it, put it into a buffer, and if you're not pressing the enter key, CP/M says, okay, I'm not going to process it just yet. Is there another keystroke from the keyboard? Okay, and we keep asking that question. But it works exceptionally well because the loop the control structure is very simple, right? While there's no keystroke, do nothing. Go back and check again. Okay? Well, that all worked well until Windows. Okay? Until Windows 3.1 came out. Now, Windows 3.1 is is one implementation of the GUI system, and what is one of the big selling feature of Windows, even the original? You can do multiple things at the same time, right? Okay, so you can, on one side you can do a little spreadsheet thing, on the other side you can do a Word document, and there was no Internet Explorer at the time. We are talking about Windows 3.1, and there was no internet to begin with during that time. Okay, so you can do Word, you can do Excel, and a few other things, and they appear to be working at the same time, quote unquote, at the same time. They only appear to be working at the same time because of what we call cooperative multitasking. In other words, one program will take control, the processor will give time to one particular program, and the program will do a few things, check a few things. It's like, oh, did someone click on the menu item? No. Did someone click anywhere on the screen? No. Well, I guess I got nothing to do. Then the program will voluntarily give up control and tell the operating system and say, hey, I got nothing to do at this point. Give it to someone. Okay? Give it to someone else so that another program can take that time and do something else. Okay? And that's why programs appear to be multitasking. They seem to be running at the same time. It's because of all of these operating systems, all of these application programs cooperating with each other. What happens when you open up a DOS prompt in Windows?
It blinks. It blinks.
It blinks, and everything else stops.
Oh, yeah. It's been a long time since I've done that.
As soon as you open up a quote-unquote DOS prompt in the original Windows operating system, everything else comes to a grinding halt. Well, why? Because a DOS prompt running this shell of DOS, and by the way, what is DOS?
Security operating system.
Disk operating system.
It's disk operating system, right?
Oh,
Yeah, I know.
You know about you.
No, actually, I actually thought it was very.
Yeah, I thought it was that.
Because I thought it was taken from like Q.
Or denial of service.
Oh.
Which DOS does sometimes, denial of service, right? Okay, but in this particular case, it is a denial of service from the perspective of the other applications, right? Because the DOS prompt is still doing its own thing of polling, okay? Is there a keystroke? Is there a keystroke? Is there a keystroke? What about the sharing part? It doesn't care. It doesn't even know that it's supposed to share. I'm the only child. I'm not going to share. Okay, no offense to any single child in this class. I'm one of 4, so I don't have a problem with that.
If you open a program, though, it gives control away, doesn't it, DOS?
Hmm?
If you open a program with DOS, doesn't just give control away.
Yep.
Everything.
Yep. And that's the problem. Okay, so when you have Windows or anything that is supposed to be multitasking, polling becomes an issue.
Does the bash do that?
Hmm?
Does bash do that?
Bash does not do that. Okay, bash is, well, it's not bash that is not doing it, it is a Unix or Linux operating system not doing it. Because what bash does is to say, give me the next keystroke. But that's a request to the operating system.
Oh.
But the operating system is the one that is not doing the polling. The operating system is saying, okay, request noted. Check the buffer. Nope, there's nothing here. But the operating system understands, well, nothing is going to come unless there's a hardware activity. And as a result, it's not going to do anything until there is a hardware activity. This program, which is on the original Atari game console, is probably also polling driven. In other words, for every single unit of time, the program is basically asking each controller on the console and say, report your position. So it's most likely done by polling as well, because it makes the program easier. Interrupt driven is harder on the software, but it's easier on the hardware. This program, being so simple, is probably done by polling and not use interrupts. In fact, the Atari architecture may not even have the hardware necessary to do interrupts.
Is that why it looks like they're never moving at the same time?
Hmm?
Well, it looks like.
No, they can appear to move at the same time. It's just that they are. You're right. Well, I think that only has to do with the screensaver
Yeah.
itself not doing it.
Yeah.
But in the actual game, they can move at the same time. Well, at least from what we see, they're moving at the same time. Yep.
Is the screensaver blanket or? Like is this the video or what?
No, this is a random thing. Just coincidentally, just kind of help out in the explanation of this concept.
No. What I meant was like, was an AI, two AIs playing that?
Yeah, it's just random. AI thing going on. Yeah. People just have too much time on their hand and decides to make screensavers that look like a really, really, really old Atari game console.
Well, just
I think I
just
can't
for
say I
extra
can come back.
information, you can play that inside of
The world of
Google
Pong.
Drive.
Yep.
Next MMO.
Sorry? So where were we? Oh, polling and bash and DOS from and stuff like that. So can you imagine on the power server, if interaction using the keyboard or anything is done by polling, what's going to happen? Not enough processing power, right? There will never be enough processing power because everybody wants to hog an entire core
Only one
just
person
by
uses at a
asking the
time.
question. Sorry?
Well, you only have one user at a time.
Yeah, that's
Only one user, no time share, one user at a time.
Yeah.
And let's check how many people or how many accounts are on power right now.
I would have, but I might have saved from that one problem. You wouldn't have that issue.
You done my programming?
Well, there are these people right next door, using power right now. I can tell because you can look at the IP addresses. They're all in C128. This is room 129. Next door is 128.
What is that?
In other words, if I type power off on the power server right now, we'll actually literally hear the screaming.
Just give it a slight pause.
Huh?
Okay.
Yeah, but then I need some help because Carol actually knows martial art.
Oh.
It will not be safe for me to walk to the parking lot. But imagine if it's all done by polling, now we'll have all of these people, at least with one shell, constantly asking, is there something for me? Is there something for me? Is there something for me? Okay? So that is obviously inefficient and inappropriate for any type of multi-user / multitasking type of operating system. Okay, what is the alternative? Going back to my office, right? My office hour, I'm waiting for someone to ask questions. Well, first of all, I'm lazy, okay? I don't want to do, polling, keep asking questions. I want to take a little nap in my office, right? Conserve energy, right? So I'm going to doze off and going to fall asleep in my office. What if someone shows up and go, hey, I have a question? You knock on the door, right?
Doorbell or something.
Knock on the door to wake me up. Okay? So you knock on the door, you wake me up, and go like, oh, okay, who is there? Can I answer your question? Sure. And so on and so forth. After I answer the question, I go back to doze off. Or if I was playing a game, I would go back to playing the game. I would just unpause the game. Obviously, League of Legends is not an option because you cannot be AFK. Okay, so in that case, it's a slightly different kind of story. So assuming I'm playing a game that can pause, I'll just go back and resume that particular game. No problem. That is the concept of an interrupt. Okay, the student who has to ask me a question is a piece of hardware in a PC that requires attention from the operating system. Now, there can be many, many different devices. Give me your keyboard. Okay, your keyboard, you just press a key, it generates a keystroke event, and the operating system is supposed to process it. Okay, that's one reason why, quote unquote, someone is knocking on the door. It can be on a touch screen. It can be a touch event. Okay, you touch something on the screen, the capacitance on the screen changes on a certain coordinate. The touch screen controller, which is a different processor, will register, hey, I see a sudden change of capacitance at this particular location. I think it needs to be processed. and it will send the information to the processor. Knock on the door, right? And then the processor goes like, okay, let me finish this first. Okay, now can I answer your question? Oh, somebody just touched on the screen at this coordinate. And then the operating system, along with the GUI, will decide what to do, okay? Network connections. Okay, your computer is constantly getting some kind of network activity sometimes, but you might say, but all of those things are scheduled because my computer is behind a firewall. So there should be no unsolicited incoming requests. But what about the response to an earlier request that you sent out? Well, about that one, my computer should be just waiting for that request to come back. Well, how long do you think a request will take to come back? Just a regular, typical HTTP request to, let's say, online banking website. You enter the URL or you click on the button on the screen. What is the order of magnitude of the response time for something like that?
Second or two.
Order of magnitude.
Yeah.
Be a couple like second or two.
It can be up to seconds, okay? But even at the quickest, it will still be measured in, okay, I'll give you guys a few choices. Nanoseconds, microseconds, or milliseconds.
Milliseconds.
At least milliseconds, in the order of milliseconds, okay?
Most websites are like 1 or 2 seconds to load.
It depends too, if you have a,
Some are
heavy,
longer.
yep, can be longer, but sometimes it can be shorter. But it will still be measured in milliseconds, right?
Yeah.
What do you think your super duper i7 quad core, hyper threading, super clock, turbocharged, running on Nitro, type of processor can do in just a few milliseconds?
Can do
Lots.
Depends what you
Right?
want to do.
Why else do you think you have a 3.7 gigahertz clock? If your processor can only do a few calculations in a few milliseconds, it will suffice using a kilohertz clock, not a gigahertz clock. So it would not be a good idea to say, hey, I just sent off this request to a website. I'm just going to busy wait for the reply. Not a good idea. So what do?
It makes you
As soon as you send out the request, you go back to the operating system and say, well, for this particular tab of this particular browser, there's not much to do at this point. Go do something else. Animate something on the screen. Run the JavaScript, on this web page, whatever, right?
Load your
Give the botnet some processing resources. There's that. Yep. So when the request comes back after a few milliseconds, what happens? Interrupt. Okay, because your Ethernet or Wi-Fi controller is going to get the packet first, and it will say, okay, I checked everything at the frame level. Everything is good to go. But your controller can only work up to a frame level. In other words, it doesn't understand TCP/IP. It does not understand HTTP. It does not understand any of those protocols. Those are all done by your operating system and the application itself. So once the frame is ready to be processed, like there's no error as far as the controller can check, it's going to knock on the door of the processor and say, hey, I just got this packet here. Do you want to process it? Okay, it may be a part of a TCP/IP. I cannot remember. It's not called a frame, but it's a fragment of a connection unit, of a transmission
like
unit.
there's frames and then inside there's packets.
Right, because TCP/IP can be order stuff. Things can arrive in a different order, and the protocol has the mechanism to resequence everything to be in order.
There's packets versus
I think they're packets, right?
Yeah, okay,
Yeah, packets. So the operating system will have to deal with the packets and reorder things back to a stream, okay? But it is done by the operating system. So your controller, your network controller, is the one who's knocking on the door and say, okay, here's a frame, do whatever you need to do with it. And then the processor at that time will basically say, I'm gonna pause my game here and do some processing with the networking protocol and be done with it, okay? That's interrupt-driven stuff, okay? Getting back to call and return, what does it have anything to do with this picture? Remember what I said? An interrupt is kind of like a hardware call or a call coming from hardware. That's exactly what it is. when your Ethernet controller gets a frame, okay, what it does is it will quote unquote call the corresponding subroutine to say that, hey, here's a frame, go do something with it. Now, the actual mechanism is a little bit more involved, okay? The actual mechanism involves an interrupt line getting driven, getting asserted, to basically tell the processor, hey, whenever you have time, I got something for you to process. When you're in the middle of executing one instruction, in other words, when you're in the process of going through the microcode of one single instruction, the processor will not get interrupted. Okay? It's only between instructions that the processor can say, okay, now I'm ready. Is there, do you, and then the processor will look at the interrupt line and basically say, okay, does anyone need my attention? If so, then it will try to identify what device is requesting, and from the device, it will be able to tell from a table where is the entry point of that subroutine that will actually, process, or handle this particular device. Now, are we still doing okay so far? Okay, it's a jump table, it's a call table. Okay?
All interrupts are going to get put into like a buffer.
What do you mean by a buffer?
Like a queue, just in case.
No, you can only service one interrupt at a time. In other words, if George is the keyboard controller and Ian is the network controller, and they're both trying to get my attention because there's a key press event happening at the same time as a frame arriving. Okay, so both of you will be asserting your respective interrupt lines. So each device kind of get its own interrupt lines. So you'll both be pressing the button. Each one of you has a button. Okay, and when I complete the execution of one single instruction, I will look through all those states of the interrupt lines, and it's prioritized. Okay. Right. So I will be looking through the list from top to bottom, and I can see the network card probably has a higher priority level. So I will see, oh, the network card needs my attention. Okay. And then I would use that information to look at a table and say, okay, where's the subroutine that can process a request coming in from the network controller? And then what do you think happens at that time? A call happens. But without a call instruction, it's triggered by a hardware setting the interrupt line, not by the execution of a call instruction. But it has the very same effect as a regular call instruction, which is to save the address of where the processor is at that time so it can resume and get back to that location. And where do you think it's going to save that information?
Stack.
On the stack. Now, I shouldn't say on the stack, because I should say on a stack. Because, and the reason why I should say a stack is because in a multi-threading, multi-processing environment, there are multiple processes going on at the same time. Each process has its own stack. But none of these processes is actually getting the stack corrupted, because the system, the operating system, the kernel, has its own stack. That is the one that it will be used to save all the information so that the operating system will know where to go back to.
Does the heap work the same way?
No, not. The heap is a whole different thing. The heap is an entirely artificial concept that is only language dependent. So only C and C++ has a concept of a heap, and it's implemented by a set of libraries related to C and C++. So that means, when the stack pointer, as far as you are concerned, is pointing here, if an interrupt happens and you're not using a protected mode operating system, then the interrupt would have used this location to store the return address of the interrupt service routine, which is, for all practical purposes, just a special kind of subroutine. When that subroutine is all done, okay, which is triggered by the hardware event, the processor will use this address and say, oh, okay, now I can resume execution to wherever I was interrupting to begin with, okay, which is your code. So by the time it goes back to your code, the stack pointer is back here. For a very brief moment that you do not know, that you're not aware of, it was down here. But by the time it returns back to your code, it's back here. But what about the content that you thought was here? That's overwritten. Okay? So even though in our case, because Linux, is a protected mode operating system, so interrupts only use the kernel stack and not the stack of your user process. So we cannot observe this stuff happening. Okay? But when you're working with Arduino, when you're working with low-level devices that have no protected mode operating system running, then you have this type of issue. What about the people who are writing code for Linux? Do they not have to worry about this anymore? It depends on which part of Linux you're dealing with. If you're dealing with device drivers, if you're dealing with kernel code, that is still important. If you're only dealing with user code, yeah, well, that's somewhat of a non-issue. Are we doing okay so far with this type of concept? With Linux now running practically on all kinds of devices, who would care about devices where you cannot fit Linux as an operating system? There are lots of devices where.
Microcontrollers, computers, and all that. That
Can
doesn't need an
someone give me
operating
an example?
Your car, or like a newer car.
Well,
Like, that might be a bit complex.
That is actually an interesting example because this is what I heard from my mechanic. In the past, on a regular, just a typical BMW 3 Series, you would have upwards of 20 to 30 computers. Okay, and each one only responsible for one little thing. Okay, one is responsible for the door locks. Okay, rolling the windows is another processor. Okay, temperature control, in the cabin is another. So they have lots and lots of these computers, networked, and they all kind of talk to each other. But you have a lot of computers. But the current trend is to replace each one of these smaller processor with a more powerful processor. So now they're going back to using a more powerful processor, but it will be multitasking. So the same one will be responsible for like door locks, windows, and say cabin temperature control. So the more powerful processors may be able to run Linux just because they have more resources available. Someone just mentioned this to me the other day. I cannot remember whom. Quad chopper controller. What is it called? This one is Pix. Chopper. There's a controller that is a.
Not that Pyrex, you're talking about like the brand of the company?
No, the product itself. But it's Arduino based. This one is not. This one does have a fairly powerful processor. But I just want to look up whether it has Linux running on it or not. Because without an operating system, you probably still have to worry about the interrupts and stuff like that happening and corrupting the stack.
I think there's a Arduino that, because most Arduinos don't have operating systems on them, but I think Yum does, or not Yum.
Arduino cannot, because I know the MCU of an Arduino, it cannot support a protected mode operating system. It has to be a protected mode operating system. It cannot be just any operating system. Okay, so it doesn't say anything about the operating system. Let me just search for that word. OS maybe? Nope, doesn't say anything about operating system. But I cannot remember who mentioned this, but there's an, okay, maybe I should just look up Arduino.
Oh, if you go to their website,
Okay, so there's Autopilot, Ardu Pilot board. Okay, so this one is based on the Arduino board, and it has the necessary controllers and whatnot to control the motors and whatnot. But underneath it is still an Arduino controller board that is doing the processing. The Arduino board makes use of the Atmel AVR microcontroller, which does not have the necessary hardware for a protected mode operating system. Now, what I mean by protected mode operating system simply means that it has the ability to differentiate between low privilege processes and high privilege processes. That has to be supported by the hardware. And the processor, this type, does not have that ability, which means when the interrupt happens, the return address pushed on the stack by the hardware interrupt is going to use whoever is active, the stack of whichever process is active at the time. Because it doesn't have the necessary hardware in the processor to say, hey, this is a privileged event. I need to use the operating system's own stack. So when you're dealing with a controller like this, you still have to think about this kind of thing and say, I cannot make an assumption that any content below the stack pointer will still be there. And we kind of doing okay so far with that concept. Somewhat? Okay. And do you think that might be related to what you may do, when you are done with school and go out there and work? It would be kind of cool to do something like this. Yep. And fly in a Yellowstone National Park. It's going to happen. It's just a matter of time, okay, before we have these drones, to basically make a whole new type of tourist industry.
There are some guys who right now what they do is they have headsets that are hooked up to quadcopters.
Yep.
And so they can fly them basically in first person, and they
Yep.
like get races. They do it out in the Bay Area.
I saw that once. I saw one person doing it in my previous air gun match, and we were all kidding about, oh, let's shoot that.
Shoot 'em down.
No, it's not really that easy to shoot it. Yep.
Yeah.
I noticed you have a module on pellet weight or something like that. One of your modules that you write,
Uh-huh.
I noticed when you have one based on pellet weight.
Pellet weight?
Yeah.
Yep. Well, there's a lot of science and math behind shooting accurately. Just ask anyone who has that type of training. It's
Oh, you
not
said pellet weight.
Yeah.
pellet,
Yeah.
as in
Like
the
little
ammo
pellets,
of
yeah.
pellet guns.
Yeah.
Yeah, there's a whole science of that thing. Right. So, are there any questions about all this stuff here, interrupts and whatnot? So we did take a really kind of detour, from subroutines, calling and returning, but it was necessary to address the question of, well, if you move just the stack pointer back up to a certain location, what about the content that it was pointing to before the stack pointer got moved? And the answer is, in certain cases, it will still be here, but you should not count on it. That is the take-home message. So is that kind of answering the original question? Yep.
We need to clean the data because sometimes they override transformer.
Say again?
Do we need to write in the code to clean this?
Do we need to
reset the data?
Reset the data.
reset the data? I don't understand. You just make sure that you don't need anything below the stack pointer, or below the address pointed to by the stack pointer. If you're not quite ready to let it go, don't change the stack pointer. Yep. All right. So if this is all okay so far, I'm going to have to delay the homework assignment, which does not mean that you should not take a look at it. Okay. I think you should get a head start, take a look at it, set it up. Even though you cannot quite do it yet, you should still do it. Yep.
Like at this point, doesn't call and return take care of the stack pointer? We don't really do
Yes, they do. Okay. So the question now is, but can we do a call and a return without call and return as instructions? That becomes the next question. Okay, does everybody kind of follow what I'm saying? What if I give you all the other instructions that we have already talked about? Okay, add, subtract, move, that sort of thing, and all the addressing modes that we have talked about: indirect, register, direct, immediate, and so on and so forth. Can we implement the call and return instructions with multiple other instructions, but without actually using call and return? That is the question.
Yeah, I was thinking, because since it has to return the address of the next instruction, right?
Right.
But it kind of, I was don't know if this goes back to what we were doing in the beginning of the class, but we have to then know the size of that instruction. Like we have to know how much that operand takes and Don't we?
Well,
because we can't just assume it's 4 bytes.
Not
after this.
exactly. Not exactly. Yep.
Well,
That's a
if
trick to
know
do.
You have the address of X, you could just move whatever value you wanted into it.
Yep, exactly. We can make a label.
Oh, okay.
Right, exactly. So what I'll do is I'm going to change this program. I'm going to just make a copy of it to call return2.s. And this time what I'll do is I'm going to implement exactly the same program, but without call and return. So I'm going to comment out this call and say, can we do something that will do exactly the same thing as a call, but without using call? Okay. Well, there are only 2 things that the call instruction will do. One, we know for sure how to do, which is an unconditional branch to wherever it's supposed to go. Okay, that one we know how to do. It's just a JMP, in this case, to F, the label. The other thing is to save the return address on the stack.
Oh, yeah, but not operator.
So we can use the push instruction, but let's say the push instruction is not even available. Well, that's still okay. We can use something to change the stack pointer, and then we can copy something to where the stack pointer points to. So the answer is yes, we can definitely do it like this, but then I will have to use up one of the registers, okay? So I'm gonna use up one register just for this purpose. So what I'll do is the first instruction. Well, I'm trying to boil down to absolutely the most risk-like instructions. In other words, I'm trying not to use any of the complex addressing modes that may not be supported by RISC processors. So this is the lowest denominator for all processors. Okay, all processors will support some kind of move immediate into a register. Should not be a problem. Subtract long 4 from the stack pointer. That's usually also supported. Okay, I'm subtracting the stack pointer by 4. And then what I'll do is I'm going to move EAX, which contains the return address, to wherever the stack pointer points to. That's basically the same thing as a push $L0. Okay, but since I'm pretending that we have really, really simple instructions because we're dealing with a RISC architecture here, it can still be done. And once we save the return address, we can now just perform a unconditional branch to F. So these 4 instructions from line 5 to line 8 is the same thing as call F. Is it cumbersome? Absolutely. Okay. On the other hand, if you have a compiler that is generating the code, who cares, right? If your processor die can be reduced to 25% of the original size, hardware manufacturers will jump on this anytime because they can save a lot of money. The yield is going to go up. And then furthermore, remember what I said? When you have complex processors, the energy efficiency is lower. Even though they're more powerful, for each clock they can do more things, but when you look at how much energy goes into multiplying 2 32-bit numbers, a cisc processor takes more energy. Yep.
Is EX even necessary for this?
Sort of, because move immediate into indirect is somewhat cisky. Cisky, yes, that's a new word now. Cisky, C-I-S-C-Y,
So
cisky.
it's not risky.
It's not risky.
It's not a risky move.
So now it is risky.
Yeah.
R-I-S-C-K-Y. Okay, the next one is going to be about the same thing, but we have to use the label L1 instead of L0. So I'm not going to bother to deal with it. What I do want to deal with is this little return statement or return instruction here. How can we do this, but without using the return instruction? Well, once again, we have to burn up one register because with a RISC architecture, everything is done by registers. So we kind of have to use up one more register. And this is a good time to also kind of talk about the number of registers for different types of architecture. The Intel architecture is a cisc architecture. It has about 8 usable registers, okay, which is okay, but by today's standard, is not a whole lot. Okay, RISC architectures, on the other hand, typically has 32 or more general purpose registers.
They'll say you have to have more.
Well, it needs to have more, but also it has room for more. because you're spending less silicon to emulate an earlier a legacy processor, and all that silicon area can now be used. Hey, we can have more registers. And there's also no legacy requirement and say, well, since we cannot change the opcode, the binary format of old instructions, and you're up and say, hey, you can implement, you can design any instruction set you want to. We will just allocate 6 bits to specify, the register. 6 bits will give you 64 possible registers. It allows you to select one of 64 instead of 4 bits, which only allows you to specify one of 16. Okay, is that making any sense? So with most RISC architectures, 32 registers is kind of like, that's okay. You get up to 64, then you go like, oh, that's good. And there are RISC processors that are even more interesting. They do not have a concept of a register. Instead, everything is put on the stack. Except one part of the stack is always cached. So it's almost as fast as regular registers, but it doesn't actually have the concept of a register. It's just that the top part, or the most recently used part of the stack, is as quick as registers, which is a kind of interesting concept. Okay, so getting back to the return instruction, what do we have to do? Well, the stack pointer should be pointing at what at this time? The return address? The return address. So let's go ahead and copy that around a little bit. We'll just use EAX again, okay? Well, once we use it, we don't need that anymore on the stack, so we can now safely say, let's go add 4 to ESP to reclaim those 4 bytes because it's not needed anymore. Now it is time to actually go back to where we came from. The address is stored in EAX. The big question is, how do we implement this? Now this is the part where I have to cheat and say, yeah, this is something that we really have not talked about. Okay? Because conceptually, it seems like that we should be able to do this. Right? Kind of. It's a jump indirect. So if you want to, you can say, oh, since it's indirect, let's put parentheses around it. That does not work either. Okay? That's the right idea. It's the right idea, but it just does not accept this syntax. Okay?
What are you saying was, is it because, isn't that technically the value, or is that still a direct address?
It depends on how you look at it. Because we want to jump to the address that EAX is pointing to.
Yeah.
So it's sort of an indirect, it's kind of like an indirect jump, okay? But the syntax does not support it. It doesn't really take this as what we want it to do. Instead, the proper syntax, which took me a little bit of time to research, is an asterisk. It's a dereference, which is kind of odd, but that's the way it works. Okay?
So it all worked out that the screensaver was all asterisks.
Yeah. They're all related, but this asterisk has 4 wings instead of 5. Yes. So line 21 is the magical jump instruction. So what it does is it does not jump to a particular static label. It uses the content of EAX to indicate the address to jump to. Okay. Now, the other thing that I can use to specify this, which is not a valid instruction, okay, this is not a valid instruction, but if this instruction is supported, it will also describe what is going on here. We are actually just literally copying EAX to the program counter, or EPC, or cancelable program counter.
It'd be nice if they got rid of the current percent sign.
Yeah, the asterisk, right?
No, I mean, we can use the asterisk since you might know it as a dereference.
Well,
I want to kind of tell you that it's a
the percent symbol is interesting in a way because the requirement to use a percent symbol as a prefix of a register means that the word or the symbol EAX is available as a label.
Yeah.
So now
so we just use EAX
as a label.
It becomes a label, yep.
Oh, okay.
So
Totally
so in terms of concept, line 21 is really doing what line 22 is doing, if line 22 is supported. But line 22 is not supported because the program counter cannot be specified as a general purpose register. And as a result, move out does not work with it. Okay, and that's an architectural type of issue. In terms of meaning, that's exactly what we want. Are we still doing okay so far? How many people still remember what a program counter is? Okay, so that means that homework assignment actually is useful. Okay, so what we'll do is we'll test this program. And gstabs-o call return.o call return.s ld call return.o gdb call return. Put a breakpoint on line 5, so we'll start from the very beginning again. Run the program, single step, single step, single step, and single step. Now we are in the subroutine F. Single step, and single step. Now here's the moment of truth because we want to know what is EAX. Okay, that looks about right. Let's double check and print the address of label 0, which is where it's supposed to go back to. It is the correct thing, okay? So the only thing remaining is, okay, is jump asterisk EAX going to do what we think it should be doing? Single step, and we are going back to label L0. So this is how the return instruction and the call instruction can be implemented without the actual instructions call and return. Now, truth be told, okay, even though from this perspective, call and return are really effectively CISC instructions because they can be implemented by smaller, individual instructions. Even in most modern, quote-unquote, RISC processors, call and return are actually implemented as instructions. Just because they're used so often, and the trade-off leads to having these instructions implemented. And the reason has to do with when you need like 4 instructions to implement one, it takes up more memory space because your program gets bigger. And 2, it takes longer because instead of 1 fetch, 1 decode to get it done, now you have 4 fetch cycles to get it done. So it is actually running slower. And that's why even with most new RISC architectures, call and return, which can be implemented using smaller instructions, they're still implemented as individual instructions for efficiency's sake. The AVR architecture used on the Arduino is a prime example. That's a very interesting architecture because it's a RISC architecture, but it would use CISC stuff when it makes sense. So it's not really religiously using RISC philosophy. It will switch to CISC when it says, hey, but this is used so often, the payoff is really worth it. Yep.
And that's only microcontroller. So a discussion of like the Pi is not related because
that is correct. The Pi is an ARM processor. The AVR architecture and the ARM architecture are very close in terms of design philosophy. So when you look at the instruction set, what is doable and what is not doable, how many registers and stuff like that, you can actually see a pretty clear parallelism between the ARM architecture and the AVR architecture, which is kind of interesting because both of those are pragmatic RISC processors. They want to get the benefits of a RISC architecture, which is a reduced footprint of the die size itself, but they still want to have a reasonable efficiency when it comes to instruction execution and execution time. So it's a good kind of like a balanced approach to designing processors. All right. So we got through call and return in this case, and we are out of time. What I really should do is when I cannot assign homework assignments, I really should use the lab time for lecture also. And I will not charge you guys extra money. Because the way you pay for the units is different. For this class, we have 3 units of lecture and only 1 unit of lab. But the amount of time for lecture is actually the same as the amount of time for the lab. So if I give you lecture also during lab time, you are actually making money.
It's a good way to look at it.
Hmm?
It has a 5-minute class.
But then you'll have to pay more. Okay, but I'll just not do that, you know. But what I'll do at the lab today, is to show you guys how to use a Makefile. Because that is a necessary utility to get the homework to work, but it's not core to the concept of assembly language programming. So I will do that part in the lab. You know, so for those of you who can make it to the lab, you know, I'll do it. I will also do the recording as well for those of you who cannot be there for whatever reason.
My dog has an appointment.